Okay, welcome back. So today we shall start with LED, light emitting diodes. Okay, till now we have studied about photodetectors and solar cells where light that falls is converted to electricity. We will start the reverse topic where you are injecting electron holes by applying a voltage and you are getting light as output. In solar cell and photodetectors, light was the input and electricity was the output, because photons getting absorbed in the semiconductor creates an electron hole pair, right. An electron from the valence band absorbs the photon, gets excited to the conduction band that is available for carrier transport. Now it creates a hole behind, right. The reverse process is that you are injecting electrons and holes and you expect them to recombine in the depletion region and recombine radiatively, so that that energy that is lost in recombining is emitted as a photon. That is the basic principle of LED. LED is also a very vast topic. There can be many courses on LEDs. We shall keep things fairly simple and we will try to understand the basic working operational principle of LED and many other kinds of LEDs. Okay. So let us come to whiteboard here. So we will talk about LED. LED is the opposite of your photodetectors. So what happens is that LED has to be a PN junction. Okay. If you look at the whiteboard here, so you have a PN junction, this is P and this is N, for example. Okay. The idea is that LED is also PN junction, a solar cell, a photodetector can also be a PN junction. You talk about this Fermi level here, and then this is your band diagram. Okay, this is your P, this is your N. Now remember that your just like photodetector, you can emit light at different wavelengths by using band gap, different band gap material which are direct band gap. Okay. So LED is always biased in the forward direction, which means you have positive and you have negative. Okay. So you bias that, then what will happen is that electrons will be injected this way, holes will be injected this way. It's a majority carrier device, not a minority carrier device like photodetector. And these electrons that go, you expect that they will recombine in the depletion region, because once they come this edge they will diffuse away. Once they come this edge they will diffuse away. You want them to recombine in the depletion region. Once they recombine in the depletion region, the idea is that if they recombine radiatively, band to band, electron and hole, you see this is your conduction band, this is your valence band. If the electron and the hole combines from conduction band to valence band, that is called band to band conduction, band to band recombination, band to band, right, band to band recombination. Okay, band to band recombination, electron in the conduction band and hole in the valence band. You are injecting hole from this side, you are injecting electron from this side. The idea is that they will recombine in the depletion region. If they recombine radiatively, this is very important term. What do I mean by radiative recombination? I mean that the energy that is lost when an electron and hole recombines, an electron will fall back from here to there, recombine with a hole. That energy that is lost band to band. Okay. If it is radiative, which means that energy lost is given away as a photon, as a photon. That photon's energy will correspond to the energy of the band edge or the band gap here, right. Then you get light emission, then you get light emission or LED. Okay, light emission or LED you get. Okay. Please remember that recombination has to be radiative and band to band. The reason I am stressing this so much is that there could be non-radiative recombination also, which means an electron and hole might recombine from the conduction and valence band, but the energy is not released as a photon. It is released in the form of heat to the phonon, the lattice vibration or any other kind of other things. That is a non-radiative recombination. It can also happen in direct band gap material if the material quality is not good. Okay. You do not want that. There could be many defect states, there could be many defects in the material in the band gap. These defects will manifest as trap states in the band gap, and these traps can also recombine, the electrons can recombine with the traps also, the holes can recombine with the traps also. Most of them are non-radiative recombination, which means the electrons and holes that you are injecting, those electrons and holes are recombining with some traps, defect states, and then because these traps and defect states will eat away the electrons holes, you can say. So then those will lead to non-radiative recombination and not contribute to light emission. It will kill your efficiency, right. The whole idea of an LED working is that you are injecting excess carriers by applying a voltage. You are having a PN junction and you are essentially forward biasing it to inject excess carriers, and these excess carriers have to recombine radiatively from band to band in order for the LED to work, because defect states can take away the electrons and holes. No, that is not good. And so radiative recombination efficiency is what matters in LED. I told you non-radiative recombinations are there. Two primary non-radiative recombinations are, one is the Shockley-Reed-Hall recombination, the trap related, and one is called the Auger. It looks like Auger, but it's called Auger recombination. Probably I have discussed Auger recombination also in one of the earlier classes, but I will tell you anyways. So this kind of recombinations will not lead to radiative recombination, not lead to light emission. They are useless, wasted recombinations of electrons and holes that you are so much injecting in the device, and that injected electron holes are basically recombining through this, then your device is waste, because you will get very low efficiency. Shockley-Hall efficiency, the recombination is with traps, recombination centers and so on. Auger recombination is a 3-particle non-radiative recombination that happens only when the carrier density is very high. Only when your carrier density is really high. What I mean by really high is that you are biasing the LED at very high voltage, so that you are getting very high injected current, and this very high injected current means that you are injecting a lot of excess carriers. If that is the case, then only Auger recombination comes into picture. If you recall EK diagram, this is your E and this is your K. What does Auger recombination mean is that this is your valence band, this is your conduction band. If you are injecting carrier, you have an electron, a very high energy electron, if the electron falls down and recombines at a hole, the energy that is lost is not emitted as a phonon, or as a light. It will use that energy that is lost to excite another electron up in the conduction band from where it was to another higher position. You see my point? The energy that is gained, or the energy that is the energy that is dissipated when an electron and hole recombines doesn't come out as photon, but it is used to excite a third electron and another third particle to go to higher energy, and that higher electron in a higher energy state will eventually come down to lower energy state by thermalization, matlab it losing energy by thermal process. So this is a non-radiative process, and this Auger recombination becomes dominant non-radiative recombination process when your injection density is high, when you have very large number of carriers, so you have n plus p plus doped layers sort of things. Okay, so that is the thing. Now you remember that essentially LED is the opposite of photodetector, right? In a photodetector, if this is your the band diagram again, you are shining light. The photon that is coming and absorbing here, the photon that is absorbed here, that is absorbed by electron from the valence band, and electron can take that photon energy and get excited to the conduction band here, conduction band, and when the electron jumps go to the conduction band, it leaves behind a hole here. That is how a hole electron pair is created, by absorbing energy of the photon. Of course, the photon energy has to be equal to or more than the energy of the band gap. A LED is the reverse process, I keep telling you, where electrons and holes that you are injecting, will recombine band to band, and the idea is that they will recombine radiatively so that they can emit light. Okay, they can emit light. Now the light can be, again, it can be visible, so as to, you mean to say it can be green, it can be blue, it can be red, orange, yellow, whatever. They can be used for display applications, many of the laser diodes and other things. Visible LED, of course, white LED is used for lighting purposes. It's a very big industry based on gallium nitride LEDs, I keep telling you. But when you talk about visible LED, that's the LEDs that are, or green, blue, whatever, the visible LEDs, you are talking about the LEDs that are sensitive to eye. That's a different ball game. You might also talk about infrared LEDs, and you might also talk about UV LEDs. But those emit light that are not visible, or the eye is not sensitive to those wavelengths. Then in that case, you cannot compare the human eye perception. There is a science of human eye perception, the vision of human eye, okay, and chromaticity diagram, like how do you perceive color, and color depends on the ambient light. All these things, how bright an LED is, what is the color you are perceiving based on the light that you are shining. For example, depending on tube light or an LED bulb, you might perceive the color of a material little differently. All those things are important only for visible LEDs, not for IR and UV LED. Okay, we'll also talk about visible LED in slightly more details because that is what is more widely used, no. But now you know that whatever be the case, an LED can be only made from a direct bandgap material. An LED can be made only from a direct bandgap material, that you know now, right. So what it means is that in an EK diagram, if you have your conduction, if you have your valence band like that, your conduction band minima also should be on the same K, so that electron hole can recombine without any change in momentum. Because if your conduction band minima is somewhere here, then electron hole recombination will have to change a lot of momentum. That momentum change makes it very inefficient, you cannot emit light. Okay, so that's why you need to have direct bandgap materials. Silicon cannot emit light. That remember. Now suppose I talk about a direct bandgap material only, like that. Okay, you see there is always a distribution of carriers here. Electrons will occupy the lowest part, holes will occupy the lowest part. The center of the distribution is not exactly at the band edge. So although the band edge or the band gap is Eg, the light emission wavelength, the energy of the photon will be slightly more than the band gap, because the electrons are distributed like this and holes are distributed like this. Okay, so slightly because at room temperature, any temperature T, there will be a distribution and there is a room temperature energy associated with it. So that's why the energy of the photon emitted is slightly more than Eg, very slightly more than Eg. You get my point, right? Is slightly more than Eg. Okay, now if I talk about the EK diagram again, this is your conduction band, this is your valence band. Okay, this is the bottom of the minima, this is the maxima, this is minima. At any point here I can write it as a this is the reference, for example this is reference. I can write the energy as EC plus H square, excuse me, K square by 2 m electron. Similarly at any point here I can write the energy as EV minus, this is going in the other direction, no, H square K square by 2 m whole. So actually the difference of the energy is this of emission, for example. So that is actually EC minus EV plus, which is the band gap. You have to subtract this from this. So that is equal to H square K square by 2 1 by m electron plus 1 by m whole, that is like the harmonic mean. Okay, so what I mean is that you can define that h nu, the photon, that energy of the photon, this is the energy of the photon that is emitted. Okay, energy of the photon that is emitted could be equal to band gap plus H square K square by 2 1 by m E plus 1 by m whole, right, and the whole thing can be written as Eg plus H square K square by 2 m r star, where m r star is called the reduced effective mass of the electron hole pair, reduced effective mass, because the electron hole pair recombining, no, this reduced effective mass can be written as m electron times m whole divided by m electron plus m whole. This is called reduced effective mass. And because you talk about reduced effective mass, because you have essentially the electrons and holes recombining from the conduction to valence band, which is slightly more energetic than the band edge. Now you use this effective reduced effective mass is used for all calculations of LEDs and other things. Okay, so you remember density of states from your earlier classes. Okay, in LED, because it involves an electron and hole that are recombining between the conduction and valence band, you can talk of them together with reduced effective mass, and the corresponding density of states is called joint density of states. What it means is that it takes into account both the electron and hole pair together. This joint density of states is called Ne. Joint density of states is called Ne, and this is equal to something like 2 times reduced effective mass 3 by 2 and then 2 pi square h bar cube into square root of E minus Eg. That means the emission will start only from energy equal to or more than the band gap. It cannot go more than band gap. Okay. So this quantity, actually if you plot this energy only from Eg, this quantity will go like parabolically. This is the density of states. That is the available number of states per unit energy per unit volume. When I talk about both the electron and the hole together using a reduced effective mass representation, it goes like that, right. Now there is a Fermi function also. If you remember Fermi function, and the Fermi function is a probability, and the Fermi function goes as e to the power minus Eg by kT. Okay. So that, or E by kT you can say. So that Fermi function actually comes something like this. This is your Fermi function and this is your density of states. It so happens that the emission, the light emission because of electron hole recombination, that emission is proportional to the Fermi function times the density of states function. Like this also gives you the number of free carriers, if you remember long back of talk about electrons or holes, but here the joint density of states basically captures both the electron and hole, their probability that they are recombining and the density of states available with them. So the intensity of light that is emitted depends on the probability of the occupancy and the product of that into the density of states, how many states are available. So if you multiply these two together, you are going to get this plot like this. You are going to get a plot like this, which means your emission is peak at an energy which is slightly more than Eg, and it turns out that this is Eg plus kT by 2, which means if you have a band gap of Eg, the emission peak actually does not come at Eg, but it comes at Eg plus kT by 2. Of course, kT is very low at low room temperature. So unless you go to slightly higher temperature, or unless you are using a low band gap material, you will not see an appreciable change. But if you use a low band gap material or go to high temperature, you will see that kT by 2 becomes important. So the peak actually emission is not at Eg, the band gap is slightly more than Eg. Okay. And please remember that there is a thing called full width of half maximum. You take this value, whatever this value is, you take the half of that value. This is the value, suppose some value, you take half the value here, and you go what is the spacing here, what is the width here, that is called FWHM, full width at half maximum. It can be on any other like PL, XRD, any other data you can use PL, full width half maximum concept. Here I am using full width at half maximum the emission. If you take that full width at half maximum emission, you will see that the value of that quantity, this this is a spacing, right. Let me use a different picture here maybe. That intensity, the intensity of the emission, which is proportional to the product of Fermi function times the density of states, it goes like this, right. This is your Eg, there will be no emission below band gap, there will be slight at higher Eg plus kT by 2 is where your peak emission happens, and your emission does not happen at one wavelength, it happens over a range of wavelength. And the full width at half maximum is this. So this is some value, you take half the value and you take the width here. This is called the full width half maximum. This is delta lambda. Delta lambda is basically the range of wavelengths over which this spectra is happening. That range, the full width half maximum, is given by this delta lambda is given by 1.8 times kT, that is the thermal energy kT, by Hc into lambda square. So if you are talking about green, lambda is equal to 520 nanometer. You plug in this and you will see some value. If you are talking about IR, red is 650 nanometer. You plug it in, you will see here some value. Red will be larger wavelength, so your delta lambda also will be large, by the way. Okay. In other words, delta lambda, this spread in blue will be lower than the spread in red, and so on. So this spread has to be there, which means LED does not emit exactly at one wavelength, or the light emission does not happen at one wavelength, which means this light emission is not monochromatic. Monochromatic means emission only at one wavelength. Your light emission from this kind of device, a PN junction and LED, is not monochromatic, it has a spread of wavelength, and that spread of wavelength is given by delta lambda, which is very small, in maybe few tens of nanometer, maybe 20, 30 nanometer, 40 nanometer. Your human eye is not so sensitive, so the human eye perceives the LED to be nearly monochromatic. It looks like it is only emitting red or green or blue or whatever, but practically speaking, if you use a very advanced tool, you will see that you are actually emitting a range of wavelength, not so widespread, but it's a spread of wavelength anyways. Okay. So this is not laser, this is not a monochromatic light, this is a spread of wavelength is there. Okay. So please keep that in mind. Okay. And this is because the density of states and the Fermi function, their product gives the probability of emission. Like this is what is the distribution of electron holes, what is the probability that they occupy, how many states are there, all these things are important. No, that is why they are giving this non monochromatic sort of a light. Okay. And this emission that happens in a PN junction I keep talking about, right. If I talk about this PN junction, this is P, suppose this is N, and I talk about that, on the P side you will inject holes, from the N side you will inject electrons, and they will recombine in here and emit light. That process of injecting carriers and emitting light is called EL, which is also called electroluminescence. We call it electroluminescence. Okay. Please remember that electroluminescence is the process where you are injecting electrons and holes. Essentially you are injecting current. Injecting electrons and holes in forward bias means injecting current. You are basically applying voltage and you are basically having a current that leads to a light emission, that is called electroluminescence. Okay. And do you know when this process of electroluminescence was discovered? It was first discovered in 1907, more than 110 years back. Okay, I will talk about that. So we shall wrap up the class here today. We shall end the lecture on LED today here. We have a lot of things to cover in LED in the next 1 or 2 classes. I will give you just very briefly the history of how LEDs had developed, where they are now, and we will talk about a little bit on the physics of radiative non-radiative recombination and how you define efficiencies of LEDs. Wall plug efficiency is a different type of efficiency. What is the use of applications of different LEDs of different wavelengths. I will talk about the losses. The loss mechanisms in LEDs are even more interesting than photodetectors and solar cell. We will talk about those, and then we will see that for visible LED which human eye perceives, you can have different kind of definitions with respect to the human eye. The scotopic vision, the chromaticity, the color diagram. We will try to see just to understand the context of LED with respect to human vision and the white LEDs. But UV LEDs and IR LEDs are not with respect to that. You cannot define brightness of a UV LED. Okay, you can only define brightness of a visible white LED sort of thing. Okay, so that's why those things we will study. We will also study about the human eye sensitivity diagram and so on. Okay, so those we will take up in the next lecture or next lectures. Okay, thank you for your time.